as we sort of get to more complex systems on chip, we'll find that one of the important things is how do we communicate between the different blocks that exist on the chip, right? And the basic notion of how we communicate within a chip is related to this idea of a bus. So let's first quickly sort of review the progression of bus architectures. Early SoCs, as I said in the early 90s and mid 90s, would be very simple shared buses with arbitration because you had a very limited number of peripherals that were connected to the bus. But by the mid 2000s, things started getting more complicated, right? We had fairly complex hierarchical buses. Why do we need a hierarchical bus? Because there can be some devices that are very high speed, for example Ethernet or video, and some devices that are very low speed, keyboard, mouse, and even the UART is actually faster than the keyboard, but still a fairly low speed device. Now as we moved into the later 2010s and today, things are even more complicated, right? So you need to have like sort of mesh networks that allow you to communicate between a large number of different peripherals on the chip, to the point where today we literally can have like such a large number of different components on a chip that you would need a full blown network on chip. What exactly is a network on chip? We'll talk about that in a little bit more. So the key drivers for this kind of evolution, obviously the most important one is the increasing number of IP blocks that are getting integrated on a chip, right? And not just that, the amount of bandwidth that is required, the amount of data that needs to be transferred per unit time between different blocks keeps increasing. You also want to have concurrent transactions. What that means is, if I have 100 different peripherals and just one shared bus, it means only 2 of them can be talking to each other at the same time. Whereas I might have a system where, let's say I want 10 pairs of devices to be able to communicate between each other at the same time, or maybe one device needs to broadcast information to 20 other devices all at the same time, right? All those kind of things are the reasons why the bus architecture started to get more complicated, right? And of course, as you can imagine, given the sheer number of such systems and the frequencies at which they operate, power efficiency starts to become a serious issue. Which means that all of these things, right, the latency versus throughput. Latency is the amount of time required for transferring, let's say, 1 byte of data, versus throughput is the number of bytes that can be transferred per unit time. They are not the same because you can effectively have a kind of pipelined transfer where I take a significant amount of time to transfer 1 byte, but after that the data starts coming at a regular speed, right, or at a very high speed. There are area overheads associated with all of these communication protocols, and of course power as well, right? And needless to say, all of this is only likely to lead to increased complexity from the point of view of what the protocol itself looks like, and you want to keep that also somewhat under control. Now ARM, as I mentioned, sort of took the lead in terms of defining the microcontroller bus architectures. The AMBA protocol family essentially is the advanced microcontroller bus architecture, right? And they have gone through multiple iterations of their design, right? It started off with the AHB and APB, which were the advanced high performance bus and advanced peripheral bus, and they would have a bridge that sort of operated between these two, right? And eventually that sort of led to what's called AXI, the advanced extensible interface, which has a lot more features in terms of what it's capable of. When Xilinx started building their sort of programmable chips and integrating processors onto it, and similarly with Altera, they essentially finally decided on using the AXI protocol as the standardized bus that could be used for communicating. That further led to sort of standardizing things in favor of the ARM driven bus architectures. Now the good thing of course is that they have made it an open architecture, meaning that the protocol itself is publicly available, and it's possible for anyone to sort of have an AXI compliant digital system that you build. Now there are even more advanced versions of this, but for most practical purposes the AXI protocol is probably what you are going to need to use at some point. Again, there are a lot of design automation tools that typically help with how to actually implement these protocols. So our purpose here is not going to be to go deeper into how exactly the AXI protocol works or how it can be implemented in hardware. We'll look a little bit at what aspects of communication are involved, but the actual implementation is something that requires some fairly careful digital design. This is what a typical bus transaction as defined by ARM or the AMBA protocol looks like, right. There is of course a clock which sort of decides the phases of the communication, and all of these things essentially you will notice that the H is sort of a generic prefix that is available, but other than that you have an address, you have some kind of control signals, you have W data which is essentially the data being written, you have R data which is the data being read back from memory, and you have some kind of ready signal that is used in order to essentially indicate whether the bus is ready to accept data or not, right. So in this case, for example, what this indicates is that maybe I am trying to write something, I give an address on the bus, right, during the address phase. So after the clock hits, there is a certain amount of time required for the data to settle down, and then A is available. I just need to make sure that A is available at least one setup time before this clock edge. Similarly, the control signals are available, whatever data I want to write is available out here, and the ready essentially indicates that yes, the bus is ready to accept data. So at this point I would then go through and finally I would get to the thing where at this stage I would have written something into the whatever peripheral it is that I am trying to communicate with, if it is memory or if it is some other kind of peripheral device. Typically what this means is that this communication, this set of signals goes from the CPU to the bus. And what is the bus? Well, it is actually just a set of shared wires along with some extra things like multiplexers and so on. But on the other side of those multiplexers are the peripherals to which you are trying to communicate. So the bus's job is only to sort of make sure that the data that you are sending, the address data and whatever is required over here, gets sent to the correct peripheral that needs to actually respond to it. Now this is typically what a bus structure itself would look like, right. The masters that we have over here, and by the way this is standard protocol, right, the master is something that can initiate a bus transaction, whereas the slave devices are things that can either be requested for data by a master or will be sent data and need to store them or process them, right. Of course this terminology is a bit problematic, it is not considered the ideal terminology, it is more like a preferred terminology today would be something like sources and destinations, right. But the master slave terminology is something that has been used for a while, so without attaching any other sort of significance to it, we are just using the same terminology here. Now obviously what this means is that if we have multiple masters, right, each of which is capable of trying to send data to one of the other peripherals, right, I need something called an arbiter whose job is to basically say, okay, it has control over a multiplexer that says I will take all the address requests from the other masters and decide which one of them actually comes out on the output of the multiplexer, right. And similarly I will take the data which is coming from the different masters and only one of them will actually be sent out, right. In the same way I will also have another kind of set of multiplexers out here that basically take the data that is coming back from the slave devices or the peripherals, right, and uses some kind of a decoder in order to decide which one of them goes back as read data. Well, the read data I can actually route it to all the masters, only the one that is looking for the data is actually going to make use of it, right. So how exactly does this arbiter get implemented? Well, that is essentially where the definition of the bus protocols comes in, right. You need to have some way by which you can decide which of the masters gets to communicate or which of the slaves gets to communicate, and therefore as long as it can control the signals going to the multiplexers and select lines, it can decide exactly who gets to use the bus at any given point in time. Now that is the most basic form of bus. What the more modern protocols do, they have essentially something called channel based communication, where you have a master interface and a slave interface, and there is an entire set of wires. So there is something called a read address channel which basically contains the read address, it contains the read write signal, it contains what is the valid There are extra things for something called strobe signals. There are select signals which decide how many of the bits on the address or the data bus need to be considered as valid, and so on. And in the you also have a read data channel which can actually be used separately from the address channel in order to send chunks of data. And as you can imagine here, as you can see here, one of the things that could be done is I could actually have so-called burst modes of transfer, where I might send one address and get back multiple words of data coming from the slave interface. Similarly, I could have a write channel where I essentially send another address for writing. I also send the data to be written along the write channel, and I have some kind of a response that comes back from the slave interface saying, okay, the data was actually received and you can now move on, right. So this notion of abstracting into channels helps to sort of define more advanced kinds of bus transactions, including bursts of data or interleaved data between different bus masters and slaves and so on, which are not easily possible using the simpler bus version. So this is part of the evolution of the bus protocols. So complying with these protocols, as you can imagine, is itself a fairly complicated thing. Many of these are so-called handshaking protocols, right. So you have some kind of a valid signal coming from one side and a ready signal from the other side that indicates, okay, whether or not the receiver is ready to accept the data. Now, it's not as though the valid always comes from the master and the ready from the slave. It could be the other way around. Let's say that the master is trying to write data, the master would provide the valid signal and the slave would then have to activate the ready signal to say, okay, it can accept the data. But let's say the master is trying to read data, then it would give a ready signal and wait for the slave interface to actually activate the valid signal and then accept the data coming from there. This kind of handshaking is essentially what allows us to define bus transactions, right? And how do those transactions get ordered? What happens when multiple devices are trying to communicate? What happens if there is a device that is slow and needs to take time to respond? Does the entire bus get blocked, or can other transactions happen during that time? All of those are defined as part of the protocol. And the bottom line is that standardizing this kind of a bus makes this level of interoperability easy. Anybody trying to design a new peripheral just needs to make sure that they are compliant with the bus protocol, and they don't need to specifically go in there and check each and every ARM processor or RISC-V processor to find out how exactly that processor would communicate. Now, the problem with buses is, as you can imagine, the more the number of peripherals, the larger the chip becomes, which finally means that you effectively get to the point where you have very long shared wires on the chip. Now, long of course is relative. We are still talking about wires that are micrometers in length, possibly hundreds of micrometers, or could be in really large chips or to the point where they are millimeters in length. But the point is, when your individual transistors are on the nanometer scale, something that is trying to signal that needs to travel across multiple millimeters or even multiple hundreds of micrometers is going to be taking something really long compared to the time required to switch across a single transistor, right. So routing such wires also becomes extremely difficult. And as a result of all of this, right, way back in 2001, there was a proposal from William Daly, who is also the chief technologist at NVIDIA now, at the Design Automation Conference, which basically said, look, rather than trying to route wires across large chips, you should be routing packets of information. And where did this idea come from? It basically comes from the domain of networks for communication, right. So this is not something naturally coming from digital design, it's more from the idea of network communications, right. And in network communication, you have the notion of what are called circuit switched and packet switched networks. A circuit switched network is something where, let's say you are making a phone call, right. Older telephones, at least, not the ones that we use today, actually had specific circuit switched connections, which means that there would be a direct set of wires that ultimately lays a direct line between your telephone and the recipient's telephone, and whatever you speak would end up going all the way through on a dedicated set of wires. But nowadays that's not how it happens. Pretty much most communication at this point is in some sense packet switched. So the data, when you speak into your phone, what's actually happening is it's getting converted into a set of packets of information sent across the radio to the nearest cell phone tower, then sent across some kind of a network to the place where the recipient is, and then finally coming back to their phone and being played over there. Now the advantage of the packet switched approach, well, there are many advantages, right? And it turns out that even in the context of individual chips, this idea of sort of routing packets rather than wires makes a lot of sense. Ultimately, it led to this notion of networks on chip. So this is sort of an abstract picture of what a typical modern network on chip might look like. As you can imagine, this is something, well, it's one way of looking at it, which is, let's say you have a CPU out here, you have a GPU, various other kinds of computational units, NPUs, DSPs and so on. You have memory blocks, right, various kinds of cache. You also have DRAM blocks. You also have all these peripherals, GPIOs, UARTs, timers and so on, right. Now this structure that I have drawn over here is what's called a two-dimensional mesh topology, right, where pretty much you have communication between adjacent devices, but you don't really have, for example, a direct communication from the CPU to the timer or the UART, right. But how does the CPU then talk to the timer? It now sends out a packet of information which gets to the nearest router. The router knows that in order to reach the timer, it needs to send it one step further out here. Once it gets to this point, it knows that probably going towards the right hand side is unnecessary, so let's go down. It gets to this point and then finally it reaches here and it has hit the timer. So as you can imagine, even sending one single command or let's say a configuration word to the timer will actually end up hopping through 4 different switches over here, which means that the latency required for the CPU to talk to the timer might have increased. It's no longer able to talk within a single clock cycle. It needs maybe 4 clock cycles to send data. Of course, it could send a whole packet of information, not just one word, right? It might be several words that get grouped together, or it might also be able to send it in a pipelined manner, meaning that one data goes and in the very next clock cycle the next value goes and so on. Now the advantage of this structure is quite simple. Let's say that there was also some other communication happening between, let's say, the GPU and DMA. This line would have been blocked, which means that in a normal bus the CPU cannot talk to the timer. Whereas in this structure, what the network would do is automatically route down to here, come here and then reach the timer through this other path, right. So it provides multiple different ways of reaching destinations, and a lot of the research around how network on chips can be improved is to sort of see how do we handle these kind of routing protocols, what should the routers look like. You don't want them to be too complex, but at the same time you don't want them to get stuck easily, right. So striking that balance is essentially where the sort of power of NOCs comes in. So in terms of design considerations for NOCs, obviously we are interested in performance at some level. That's why we want to get low latency as well as high throughput, right, on large systems. We want to be able to manage things like congestion, the example that I gave where let's say there's already some communication happening on one particular link. Can I route around that link and can I make sure that things don't get too congested? And you can also interestingly provide certain things like quality of service. If you, for example, in this wanted to give very high priority for communication between the CPU and let's say the SRAM, I might give higher quality of service, which means that any packet destined for the SRAM gets a higher priority than something that's let's say destined for the UART. And therefore, the router would then appropriately decide either to just buffer the other packets until there is extra time, extra bandwidth available on the link, or possibly even just drop the packet and the CPU needs to retry communicating with the UART, right. So various kinds of protocol differences that have already been fairly well studied in the domain of networks can now be brought into play even inside a single chip. All of this is fairly complex, which means that you need to do a lot of power optimization, right. And there are various kinds of things that we need to do ultimately in order to improve the power consumption, some of which we will discuss briefly as we move forward. And there is also this notion of the area itself. As you can imagine from a diagram like this, each of these routers is now going to occupy a certain amount of area. Is it worthwhile? Is this a better trade-off than just having long shared buses across these systems? Is something that we will need to actually analyze carefully while building such systems. So that in turn is handled through various ways: the router complexity, the sizes of buffers, which in turn directly impacts the area that is available, the width of the link. By having more wires on a particular link, it means that the bandwidth is improved on that link. Does that make sense for a particular set of connections? Or you might find that there is a particular channel or a link with a high bandwidth, which means that I can now create multiple virtual channels within it by sort of sharing the bandwidth across multiple different communication packets. Now all of this also leads us to another interesting or important concept called the clock domain crossing, right? As you can imagine, in a system like this, it is very unlikely that all the systems out here are working at exactly the same speed. In particular, you can pretty much be sure that the UART, GPIO and some of those devices are going to be working at very different speeds from, let's say, the cache memory or the DMA block, right? So if that is the case, we definitely have this notion of where we want to communicate between different blocks, and that communication needs to cross the clock domains, right? An example of that could be, I define something called clock domain A, where this clock is running at 100 megahertz. I also have clock domain B, where the clock is operating at 75 megahertz. Now imagine that I have a flip-flop with clock A talking to a flip-flop with clock B. I can do all the analysis over here that I want in terms of what is the the combinational delay between these two. The problem is the clock edges over here are never guaranteed to be synchronized, right? Which means that if I have a signal coming through from here, right, I can always end up at some point having a setup violation on the flip-flop for B1, right? It's impossible to guarantee that that cannot happen, for the simple reason that the relative phase or the point at which the clock edges happen here versus the clock edges happening here are themselves changing with time, because these two clocks are at different frequencies, right? So if that is the case, there is a possibility always, even if you have taken into account that there shouldn't be any combinational delay and so on, that you end up with some kind of a setup or hold violation at this FFB1, right? Now what that in turn means is, I am assuming of course that this is neg-edge triggered. You could easily as well have been pos-edge triggered, that doesn't make any difference, right? But what happens in this case is, I am going to see that because there is setup violation over here, possibly the output of flip-flop B1 goes into metastability and takes a certain amount of time before it stabilizes, right? But what I can be sure of is that even if that happens, by the time it reaches the next clock over here, right, flip-flop B2 will pretty much only not see this setup violation. It will see something which is reasonably close to a logic 0 or a logic 1, because enough time has been given for this data to settle before it reaches here, because B1 and B2 are working with the same clock. So even if B1 went unstable at one clock edge, that is not going to affect the next clock edge at B2. With that in mind, effectively this is what's called a double flop synchronizer. All that it does is make sure that metastability does not get seen in the destination domain. It is stopped at this boundary flip-flop, and by having some kind of an extra flop over here, you are able to settle this to either a logic 0 or a logic 1, and you don't have the problem of sort of signal endlessly fluctuating with time, right? So this kind of thing, clock domain crossings and synchronizers, are important in any large design. So to summarize our discussion of the on-chip communication, there are several different protocol standards that are popular these days. AXI is typically used for high performance peripherals or interfaces. Variants of AXI, typically still the APB, the advanced peripheral bus, right, is used for low power peripherals or low speed peripherals. But modern systems which typically have multiple cores and are multiple different peripherals tend to require NOCs, networks on chip, to handle all their communication. There are several critical design considerations, some of which are performance requirements. Just the interconnect, the communication interconnects can often be determining factors for the performance. They are the bottleneck that determines how fast the system can transfer data. At the same time, the sheer amount of switching activity that is happening on these large buses, long wires, means that there can be significant power consumption in the communications infrastructure itself, right. That in turn means that one aspect of the design process, which is typically called physical design, which is one of the things that you study when you look more into the aspects of digital IC level design or VLSI design, right. But we have sort of not got into it here because we are not talking about design at the level of transistors in this course. However, this physical design process does get significantly impacted by the need for sort of laying out these large wires and the kind of capacitances that we are dealing with. Not just that, all of this also leads to increases in the complexity of the verification process itself. How do we know that what we have implemented is going to work correctly? Moving forward, one of the things that we can expect to see is some level of increase in the heterogeneity, right. We would like to have homogeneous interfaces, and that is sort of where the network on chip architecture went. But if you look at it, when you have peripherals with wildly different sort of requirements in terms of bandwidth and throughput requirements, you probably also want to just make the interconnects different from each other so that they can each be optimized for the kind of bandwidth and data that they need to handle. There are some kinds of specialized protocols for emerging applications, especially there are a number of newer things for AI ML. There are other kinds of things such as in-memory computation and so on, which also require specific, which will benefit rather from specific custom kinds of protocols. There are many interesting research topics on how you can use ML kind of techniques for optimizing the layout as well as operation of NOCs, and of course more advanced kinds of technologies, right. Are there other kinds of ways by which we can sort of literally move closer to the speed of light in terms of how we can switch data around by moving to things like photonic interconnects?